And here we go.
10.
Hydrogen burn-off igniters initiated. 7, 6, 5. 4-stage engine start. 3, 2, 1. Boosters in ignition. And liftoff of Artemis I. We rise together back to the moon and beyond.
When people hear NASA's most powerful rocket, they often picture a single dramatic launch and then move on. The Space Launch System, or SLS, is more interesting than that. It's a whole strategy in metal, software, plumbing and politics, built around one goal: sending the Orion spacecraft and eventually crews beyond low Earth orbit with enough performance margin that NASA can take fewer risks in assembly, fewer launches, and fewer, if everything goes perfectly, steps. SLS is a super heavy lift rocket designed to push large payloads, and especially the Orion crew vehicle, out of Earth orbit and towards the moon. NASA describes it as the backbone of their human lunar exploration program, because it can send Orion towards the moon directly in one launch without needing multiple launches just to assemble the mission in orbit. That one launch idea is a big deal because every extra launch adds extra chances for something to go wrong, and every extra docking and assembly step adds complexity. If you can lift more in one go, you can keep the mission plan simpler. SLS didn't appear from nowhere. It was established after the NASA Authorization Act of 2010. And it grew out of a set of design choices that tried to balance a few competing pressures. NASA wanted a vehicle that could be human rated, meaning it could meet safety and reliability expectations for carrying astronauts. They also wanted something they could realistically build using existing American industrial capabilities. This is why when you look closely at SLS, you keep seeing familiar names and familiar hardware. The RS-25 engines, for example, that once flew on the Space Shuttle, and solid rocket booster technology that also comes from Shuttle heritage, but enlarged and updated. SLS is new, but it is new in a very deliberate way. Now let's picture the rocket as a stack. At the bottom you have two solid rocket boosters. Between them is the core stage, which is the tall orange cylinder that stores cryogenic propellants, houses the avionics, and holds 4 IRIS-25 engines at its base. Above the core stage is an upper stage called the Interim Cryogenic Propulsion Stage, or ICPS, which provides the in-space push that sends Orion onto its translunar trajectory. Around and above that upper stage are a set of adapters that connect different diameters together, protect equipment and provide separation systems, and at the very top is Orion. That description sounds straightforward until you notice what it implies. This is not a single engine and a fuel tank, it's a coordinated system where different propulsion types do different jobs at different times, and where separation events are not side details but central to how the mission works. In the Block 1 configuration, which is the early version used for the first Artemis missions, SLS stands about 322 feet tall, or roughly 98 metres. At liftoff it produces around 8.8 million pounds of maximum thrust, and it gets to space in a little over 8 minutes. NASA has described this as about 15% more maximum thrust than Saturn V produced during launch and ascent, which tells you the class of vehicle we're talking about.
Boosters are larger for SLS because we needed more thrust at takeoff. This is a much larger rocket. Trying to go to the moon is a much harder job than trying to go to the space station in terms of the physics of the problem. So we produce a lot more thrust than we did under Shuttle, and so we added a 5th segment in both boosters, and that gives us the thrust needed for these Artemis missions. So we test these in a remote test site out in the desert, and we do that for safety reasons. In fact, we watch them from 3 miles away, actually, from the test itself. But it's in what we call the T97 test stand. Northrop Grumman does these tests for us out at their Promontory plant in Utah. They've done these for years and years. They use the same stand under Shuttle, though we've had to do some changes to it for our booster for SLS because it's larger.
T plus 5 seconds. T plus 10 seconds.
Hi, my name is Nicholas Chaston, and I'm the ballistics engineer in charge of predicting motor performance for the Flight Support Booster 1, FSB-1. Here at the Northrop Grumman's Promontory, Utah facility, we manufacture the solid rocket boosters for NASA's Space Launch System that will launch Artemis missions to the Moon and beyond. Today we are testing one of those boosters in our Promontory test area. The SLS booster motor measures 167 feet long and 12 feet in diameter. We have successfully completed 5 previous tests to qualify for flight. This test, dubbed Flight Support Booster 1 or FSB-1, will evaluate new propellant materials and verify that all ballistic requirements of the motor are met. Preparations for this test began in March. The first of 5 segments was installed in the test bay in April, and the last one completed installation in June. The motor has been cold conditioning to a target temperature of 60 degrees Fahrenheit to 70 degrees Fahrenheit over the last several weeks. All of our large solid rocket motors undergo ground tests at our Promontory site before ever flying. In addition to holding this 1.6 million pound motor in place, the structure houses all necessary electronics and instruments needed for motor firing and gathering performance measurements. Ground tests such as these give us the opportunity to collect additional data parameters on the performance of the motor that would not be possible on a flight. Upon ignition, the motor at this target temperature will fire for about 122 seconds and produce 3.6 million pounds of thrust. The 5-segment SLS rocket booster is the largest solid rocket motor in the world.
But thrust is only half the story. The reason you build a rocket this large is not just to make a loud cloud at liftoff, it's to carry mass and volume. With SLS, NASA is buying the ability to launch Orion, its service module, and the hardware needed to push it towards the Moon, all together without having to break the mission into smaller pieces. With SLS, NASA is buying the ability to launch Orion, its service module, and the hardware needed to push it towards the Moon all together, without having to break the mission into smaller pieces. This is also why NASA designed SLS to be evolvable. Block 1 is the beginning, not the end, and later versions like Block 1B are taller, heavier, and built around a new exploration upper stage, increasing capability and adding a universal stage adapter cargo compartment. NASA's own reference material puts the Block 1B crew configuration at about 366 feet tall, compared to Block 1's 322 feet. The core stage is the largest rocket stage NASA has ever built. It's roughly the same diameter as the Space Shuttle external tank, and that is not an accident. Keeping that diameter meant NASA could reuse experience, tooling knowledge, and even facility capacity from Shuttle and earlier programs. The core stage holds liquid hydrogen and liquid oxygen, feeds those propellants down to 4 RS-25 engines, and runs for roughly the first 8 minutes of ascent. This is also where a lot of the brains live, because the core stage avionics connect to the boosters, engines and upper stage systems and coordinate the whole vehicle's behaviour. Cryogenic propellant sounds simple until you remember that liquid hydrogen must be kept extremely cold, and liquid oxygen also has to stay cold enough to remain liquid. That is one reason the core stage is covered in thermal protection. The orange colour isn't paint. It comes from spray-on foam insulation that protects the propellants and helps manage boil-off, while also handling aerodynamic pressure as the vehicle accelerates through the atmosphere. Over time, sunlight tans the foam into that signature orange colour people associate with SLS. The thermal protection system is both practical engineering and it looks pretty cool. At the bottom of the core stage sit the 4 RS-25 engines. These engines are quite significant because they represent a certain philosophy. NASA could have chosen to design a completely new main engine from scratch. Instead, they adapted an engine with a deep history of testing and flight. The RS-25 is the former Space Shuttle main engine, and it has enormous accumulated experience from shuttle missions and ground testing. For SLS, the RS-25s use updated controllers and operate at higher thrust levels than they typically did in the shuttle operations. They ramp up to full power and the boosters light at T-0, which is the moment we call liftoff. From that point, the vehicle rides a carefully planned throttle schedule. It's not just full power the whole way. There are times when the engines throttle down to reduce stress during max aerodynamic pressure, then throttle back up, then throttle down again to manage loads around booster separation, and later to manage G-forces as the vehicle gets lighter. This kind of choreography is how you keep a giant rocket inside its structural limits while still hitting your target trajectory. But the RS-25s are not doing the heaviest lifting at liftoff. That job belongs to the solid rocket boosters. SLS uses 2 5-segmented solid rocket boosters derived from the shuttle's 4-segmented design, but enlarged. Those extra segments, along with design changes in installation, avionics and nozzle configuration, are why SLS can push heavier payloads towards the Moon than Shuttle ever could. Solids are brutally simple in one way. Once they're lit, they burn until they're done. You can't turn them off like you can with liquid engines, and that is why they are built and tested with such care. From liftoff, the boosters supply the majority of thrust for the first couple of minutes. They burn hard and then they separate at around 2 minutes into flight, when the vehicle is already high in the atmosphere and moving very fast. Booster separation is a carefully engineered event involving pyrotechnic separation belts and small separation motors that push the boosters away so they don't collide with the core stage. The boosters are then spent and fall away, and SLS continues upwards on the RS-25 engines alone. Once the core stage has done its job, you reach another major transition. The core stage separates and the upper stage takes over. In Block 1, that upper stage is the Interim Cryogenic Propulsion Stage, or ICPS. This is a modified version of a proven commercial stage based on technology used in the United Launch Alliance's Delta IV family. ICPS uses liquid hydrogen and liquid oxygen and is powered by an RL-10 engine, a model line that has been flying in different forms for decades. In the Artemis profile, ICPS performs the burn that sends Orion onto a path to the Moon. It's the part of the stack that turns "we made it to orbit" into "we are leaving Earth orbit" that is a very difficult job, and it happens after the most violent part of the launch is already over. Around the ICPS and above it are adapters that do several unglamorous but vital tasks. One of them changes the diameter from the wider core stage below to the narrower upper stage above, while also protecting the internal system from vibrations and acoustics during ascent. Another adapter sits between SLS and Orion, and for Artemis I it also carried CubeSat payloads. These tiny spacecraft were not just extras, they were part of the mission's broader value, because they allowed NASA and partners to send small science and technology demonstrations into deep space alongside the primary mission. This is a pattern you'll see often in modern spaceflight, piggyback payloads that take advantage of a big rocket's margin. So far we've described the parts, now we need to talk about what makes those parts behave like one vehicle. That's avionics and software. It's tempting to treat avionics as a footnote, but for SLS, avionics are the difference between power and control. The core stage flight computers take in data from sensors across the rocket, including distributed avionics in the engines, boosters and other sections, and then they command engine gimballing, manage guidance and navigation, handle telemetry and support range safety functions. NASA's own SLS avionics material makes the point quite clearly. Getting to space in 8 minutes is not only about thrust, it's about coordination, timing, and reliable computation under extreme conditions. This is also why the testing story matters so much. Before SLS ever flew, NASA ran extensive testing at different scales and levels of integration. There were lab environments where engineers could run thousands of virtual missions, pushing flight software through simulated wind, weather, and vehicle behaviour. There were structural tests using heavily instrumented test articles to validate computer modules. There were wind tunnel tests that looked at airflow and heating as the rocket pushes through the atmosphere. There were acoustic tests on scale models to better understand how vibration and sound might affect hardware and in future missions, crews and payloads. All of that work exists because rockets don't fail politely. If something is going to surprise you, it will do it at the speed of sound, with enormous forces involved. So it's better to be surprised in a lab than on a launch pad. Then came integrated testing, which is where engineering becomes almost theatrical. When SLS was assembled in Kennedy's Vehicle Assembly Building, NASA ran an integrated test and checkout campaign that aimed to test the full system end to end. That includes powering up, checking communication, verifying that avionics talk properly, rehearsing countdown operations, and practicing cryogenic propellant loading in wet dress rehearsals. This kind of testing is as much about human procedure as it is about hardware. The launch is not just a rocket event, it's a whole team event, where controllers, technicians, software, valves, sensors, and ground systems all have to hit their marks in the right order. The other big test campaign that deserves attention is the Green Run. The phrase Green Run means the first time you run a new stage as a complete integrated system, like you would in flight. For the Artemis I core stage, that culminated in a hot fire test at NASA's Stennis Space Center, where the stage was loaded with propellant and the RS-25 engines were fitted while the stage was held down in a test stand. This gave engineers a flight-like dataset on how the core stage behaves as a whole machine. That matters because the core stage is new in a way that the engines are not. Even if the engines have heritage, the way they are mounted, fed, cooled and controlled in this new configuration is different.
The Green Run Hot Fire Test with the Space Launch System or SLS rocket's core stage for our Artemis I mission is now targeted for as early as January 17th. The Hot Fire is the 8th and final scheduled test of the Green Run series and will see all 4 of the rocket's engines fire to simulate a launch. We conducted the 7th test of the series, the wet dress rehearsal, on December 20th. During that test, the core stage tanks were loaded with more than 700,000 gallons of super cold propellant for the first time and then drained. SLS will launch an...
All of this testing leads to a question people rarely ask out loud. How do you even move something like this? SLS is so large that transportation is part of the engineering story. Different components travel in different ways. Engines can move by truck, booster motor segments can move by rail. But large stages and adapters require specialised carriers, including aircraft and ships. NASA has used the barge Pegasus, originally built to transport Shuttle external tanks and modified to handle the longer SLS core stage.
Good morning. Welcome to NASA's barge, the Pegasus. My name is Joseph Robinson. I'm the Marine Operations Manager on board. It's my job to ensure that the barge is ready to go at a moment's notice for NASA. The barge is 310 feet long. It's got a 50-foot beam. It's specifically built to ship the core stage. We ship parts from here to Huntsville, Alabama, all the way down to Kennedy Space Center. It's a unique platform, and the crew is nothing but the best.
My name is Jeffrey Whitehead, and I'm the AB on the barge Pegasus. What I do on here is the same thing that you would see a captain doing on any other marine vessel. I manage the deck crew, and I work as a team with the engineer on here to make sure that the barge is ready to go and ready to ship the rockets.
Scott Leday, marine engineer aboard the NASA barge Pegasus. When I came here to do this, I take it a little more personal. It's a wider scheme and less room for error than on another vessel. I mean, you're working with a rocket that everybody has poured their heart and soul and took time away from their family to come out and work on it. You don't want anything to go wrong.
Stennis to KSC is a pretty nice trip. We have a couple tugs that'll latch onto us over there up at Stennis. We'll come out the locks and we'll head south on the Pearl. We got the little Wrigley's Bridge and we'll come out the Mississippi Pass and we meet up with a seagoing tug out there. He'll hook up to our bridle. He'll drag us all the way down to the Florida Strait and take us out to the east coast of Florida back up. It's usually about a 6-day trip, and then we get up there and a couple tugs grab us and they bring us on into KSC. We actually monitor every aspect of the trip. The people at NASA know the wave heights, they'll know the temperature outside, they'll keep up with the movement of the barge, how much of a list we had to the port or to the starboard or from the bow to the stern. And all that is constantly being monitored and updated. Beautiful water, fun trip. We always have a good time. I mean, good fellowship out there talking with the guys. You really get to know each other when you're just sitting out at the ocean like that for a few days. When people come here and they look at this barge, I mean, it's a reflection of us and how well we work together and how hard we work.
The ICPS is shipped by sea using ULA's cargo transport ship. NASA has even used its Super Guppy aircraft for certain hardware movements. When you see the rocket on the pad, you are seeing the end of a logistics chain that crosses states and involves custom fixtures, lifting operations and transport planning. Even the rocket's exterior markings have a purpose beyond looking official. Alongside the USA flags and the NASA logos, SLS and Orion carry photogrammetric markings, like checkerboards and high contrast shapes. These are used as visual reference points for engineering imagery so analysts can track motion, alignment, and separation behaviour by studying high-speed video. When a booster separates or when a stage adapter jettisons, NASA wants to compare what actually happened to what computer models predicted. Those markings turn video into measurements. They are a quiet example of how modern spaceflight is built around data feedback loops. Now we should connect all of this back to Artemis because that's the reason SLS exists. Artemis I was flown in 2022 and it was the first integrated flight of SLS and Orion. This flight was uncrewed. It was the mission where NASA proved that the full stack could launch and send Orion on its lunar trajectory. That success sets the stage for Artemis II, which is the first crewed flight of SLS and Orion. The crew is made up of Reed Wiseman, Victor Glover, Christina Cook, and Canadian Space Agency astronaut Jeremy Hansen. As of late February 2026 reporting, Artemis II has been described as targeting no earlier than April 2026, after additional technical issues and launch processing challenges with NASA working through repairs and schedule updates. Different outlets describe the delays with different emphasis, but they agree on the basic point that the mission's launch date has shifted and is sensitive to hardware readiness. So it's worth reflecting on why Artemis II is such a big moment. It's not a landing, it's not a test flight. The mission is meant to demonstrate that the systems work with people on board, beyond low Earth orbit, with the communications, navigation, life support and operational rhythm that a deep space mission demands. In a way, Artemis II is NASA proving that they can safely do the boring parts of lunar exploration again. The long coast, the deep space operations, and the high energy return to Earth. In the history of spaceflight, those boring parts are exactly where small issues become big emergencies if you're not properly prepared. Block 1 is not supposed to be the final form. NASA's published references describe the move towards Block 1B, which adds the exploration upper stage and increases performance and flexibility, including more room for cargo carried alongside or beneath Orion, depending on configuration. The larger message is that SLS is not a single rocket but a family plan, aimed at supporting repeated missions where the ground system, interfaces and operational knowledge can remain consistent over time. You could see SLS as a trade. NASA chose a design that leans heavily on proven propulsion heritage, updated and scaled up, combined with a brand new core stage and a modern avionics and software architecture. They built a rocket that is enormous and powerful because they want mission plans that are simpler and more robust. They tested it with an intensity that reflects how unforgiving launch and deep space are. They built logistics chains to move parts the size of buildings, and they embedded measurements into the rocket skin so that every flight can teach them how to improve the next one. SLS isn't perfect and it's not immune to delays or debate, but as an engineering object, it's an attempt to make deep space crewed missions less like stunts and more like operations. If Artemis succeeds in building a steady rhythm of missions, SLS will have been one of the core tools that made that possible, even if it never becomes as familiar to the public as the Shuttle once was. And when Artemis II finally lights its engines with a crew on top, you will not just be watching a launch. You will be watching the moment where a decade of design choices, testing, logistics and software finally has to work in the only environment that counts: the real sky.